So definite integral and the area beneath the graph. So if we have some graph between A and B, we're looking for the area, and the area turns out to be this definite integral. Now to evaluate a definite integral, we need this fundamental theorem of calculus. Now, the fundamental theorem of calculus tells us that if capital F of x is an antiderivative of little f of x, then the definite integral from a to b of f of x dx is equal to the difference. Just evaluate the antiderivative at the two endpoints and take the difference, and that'll actually, remarkably, give us the area beneath that graph. A really neat thing that works out. That actually gives us the area beneath the graph. And that's called the fundamental theorem of calculus. And now we want to look at first. Okay, well, how do we use this? How do we use this? How do we actually now apply this? Okay. Questions? So, for example, let's say we want to find the integral from 0 to 4 of x squared dx. The process we use and the notation we use is we'd first, okay, what's the antiderivative of x squared? What's an antiderivative of x squared? So we go through the process of finding the indefinite integral, just like we would have done before, just like we did a few minutes ago. So that would become 1/3 x cubed. Now normally for a indefinite integral we'd have the plus c there, so we get the family of derivatives. But we need only one antiderivative, so we can pick whichever one of the millions, infinite number of ones there are. So we pick the one where the constant's 0. And then the notation we use is a little bracket, 0 to 4. And what that notation means is we're going to take it and evaluate it at the top number, and then subtract off what we get when we evaluate it at the bottom number. So that would be 1/3 times 4 cubed minus 1/3 times 0 cubed. So the definite integral there is 64 thirds. 64 thirds. So computing these definite integrals really isn't that bad. Really isn't that bad. It's just that extra step of now evaluating it at the endpoints. Like I said, quite remarkably, what it does do is it actually finds that area beneath the curve.